All right, guys, welcome back. So we're going to do a laboratory experiment to help us kind of get back into things with basic kinematics. So let's start out by talking about some background information for the lab. So if you go into my OneNote and you switch over to chapters 2 and 3, which is the section we're going to be working on for the next couple of days, you can see the first page here is our drag force lab notes. And I just want to go through these with you guys. So in this lab, we're going to take an object and we're going to try to determine a relationship between the object's shape, the velocity it's traveling at, and the amount of air resistance that it feels. So let's do a little bit of review here. So first, we've got Newton's second law. So Newton's second law says that the net force acting on an object is equal to mass times acceleration, which is the same as saying mass times the second time-based derivative of the position, and here x position, since we're going to do one-dimensional. You could use y if you want as well, because it's vertical. It doesn't really make a big difference as long as we set our coordinate axis up so that x is along the vertical. Whatever you like is fine. So we would here label downward as being the positive x direction if we were going to have it notated like I do in the notes. The way this lab is going to work is that we're going to do most of our analysis at terminal velocity. Now, terminal velocity is a phrase that physicists use to describe the point when an object in free fall is no longer accelerating. Now, we know from, again, Newton's second law that if an object is not accelerating, the net force on the object must be equal to 0. I should say 0 newtons. Combination of Newton's second and first law. So if we've got an object falling at a constant rate, then it's not accelerating, and the net force acting on that object is 0. If we draw a free body diagram here quickly, we can very quickly pick up on the fact that in free fall, the only forces acting on this object would be gravity and air resistance, which we're going to call our drag force. Now, using Newton's second law, we have a summing equation in one dimension that gives us the force of gravity acting downward in the positive direction. That's just how I defined my coordinate system. And air resistance acting upward in the negative direction. And this should not have a little vector hat over it because we've pulled out the negative sign for the direction. Okay, so, and that's going to be equal to our mass times our acceleration, which we want to be equal to 0 at terminal velocity. So during this experiment, what we're going to do is we're going to say if the velocity the object is falling at is its terminal velocity, then the object's weight will be equal to the drag force at terminal velocity. And that's going to help us do some of this analysis. Now, one thing that you might not be aware of is the drag force on an object depends on its shape and the fluid that it's moving through, in this case air. And we can have different drag forces that depend on velocity directly. It could depend on velocity squared, or it could have some other more complex dependence on velocity. But the main thing to remember here is that the drag force of an object moving through a fluid is dependent on its velocity. And this is our first real look into a differential equation. It's an equation where, in this case, the force acting on the object is, we know force is mass times acceleration, and the force that we're getting out of the air resistance is dependent on velocity. Well, velocity is the first time-based derivative of position, and acceleration is the second time-based derivative of position. So there's a really interesting relationship here where the force that we feel is based on the velocity that we're traveling at. You see stuff like this, especially with things like tennis balls and Nerf guns. Nerf guns can have extremely high muzzle velocities for their darts, but the darts are designed in a way so that they twirl as they move through the air to maximize their drag and slow them down so that they have a very low terminal velocity. So they start at a very high velocity and then move down quickly towards their terminal velocity. Tennis balls, the fuzz on a tennis ball is designed specifically to counteract the high velocity that you get from professional tennis players' serves. And actually NASA was one of the corporations or industries or whatever you want to say, organizations that were working on helping design a tennis ball that would reduce the rate that serves let me say that again, reduce the maximum terminal velocity of the tennis ball after a serve, because they didn't want matches to be determined solely based on whoever could serve the fastest and not allow their opponent to have any reaction time at all. Also not very fun to see that happen over and over again for the audience. Anyway, so you guys, during the lab, you're going to have two different sizes of coffee filters, and those are going to help you run the experiment and see the difference between the size and shape of objects. You might know just based on common sense that an object's air resistance changes based on its shape. If you have a tissue, take a tissue and throw it in the air, and it has a very low terminal velocity. It's going to very quickly slow down and reach its terminal velocity, and it, in turn, will not travel very far away from you. If you crumple up the tissue and throw it, it's going to travel farther because it'll be able to reach a higher terminal velocity. You'll have less drag force. All right, anyway, let me talk to you a little bit about the mathematical analysis that you'll need to do for this lab. Number one, you guys are going to be using a motion detector to graph the motion of a coffee filter in free fall over time. Here's an example of what that graph might look like. Now remember that this is a position time graph, and because the graph is curved, we know that we're accelerating. Remember that the slope of the position time graph is velocity, and if we have a curve, that means the slope is changing continuously, and that means that we have acceleration in this region. There will be a point during the coffee filter's descent where the rate of change of the position becomes constant, the velocity is constant, and you'll see the graph start becoming more linear. That's the area of the graph we're interested in. We're going to look at the linear region of the graph and use Logger Pro to determine that velocity or that slope. You're going to do that for several trials so that you can avoid experimental errors. So don't just do one trial. Do it several trials and make sure that you're getting similar terminal velocities. Next, we need a graph that can give us a relationship between our drag force and the velocity we're moving at. And the way that we're going to do that is we're going to manipulate weight so that we can get a proper relationship. So at terminal velocity, we found that the weight of the object is equal to the drag force. We can manipulate the weight as our independent variable by changing the mass of the coffee filter. The way you're going to do that is you've got your coffee filter. It's a terrible looking coffee filter, but you're going to take your coffee filter and you're going to put another coffee filter in it. Let me draw this differently. Erase. So we'll take another coffee filter, put it inside that coffee filter, doubling the mass of the coffee filter. And the nice thing about this is we won't be changing the shape. The shape is what we want to keep as a constant because the drag force is determined by that shape. So we can alter the mass without changing the shape, and that'll leave isolate that variable from changing. If we rearrange this a little bit, what we'll find is we're going to guess that our drag force is dependent on the square of the velocity. So at terminal velocity, we should find a relationship where the weight of the coffee filter is equal to some unknown constant times the terminal velocity squared of the coffee filter. And if we solve that, we get this relationship. What this relationship is telling us is that if we make a graph of our terminal velocities with respect to mass, or weight, and we plot them in log or pro, we should get a relationship that is 1 over c. So if we guessed properly, we should get a straight line, a linear relationship, and the slope of that line is 1 over c, and that'll tell us our constant. If we guessed wrong and the drag force does not depend on the square of the velocity, then what we'll get is a curve up or down, away from linear, and that's going to tell us that we need to maybe try something else. Try just velocity, or try the cube of velocity, or something else entirely. But start with those: velocity, velocity squared, velocity cubed, and see if you can get one that gets close to linear. Also, when you're doing your curve fit, there are two different fits. There's a linear fit and a proportional fit. Linear fit is going to allow the fit to pass through a non-zero y-intercept. Now, this doesn't make any physical sense because this model, this linear model, would be telling us that when the weight of the object is 0, its terminal velocity is something other than 0. But we know that if an object doesn't weigh anything, it's not going to be in free fall. It won't fall down. So that would be a model that is incorrect. So we want to use proportional fits and make sure that our intercept, our y-intercept, is through 0. Okay. Let me talk to you a little bit about setting up your experiment properly so that you can get accurate results. The first thing that you're going to want to do is eyeball how high does the coffee filter need to be dropped from to reach terminal velocity. And you should do this for several different amounts of coffee filters. You need to make sure that it reaches terminal velocity. Let's say that we're going to do 6 trials. That means by the end, we've got 6 coffee filters in here, and we need to make sure that however high we're releasing this coffee filter from, that it can reach terminal velocity by the time it hits the ground. And we want to figure this out first because we don't want to get 30 minutes into the experiment and determine that we haven't been releasing it from a high enough height. Next, it is better for you to place the motion detector up top here than on the ground. So you may want to think about using a ring stand, maybe over the edge of a desk, and let the coffee filter fall down towards the floor. You want to make sure you don't start the coffee filter in the dead zone of the motion detector, and you want to let the coffee filter fall away from the motion detector. There's a very important reason for this, and it's because as the coffee filter gets towards the ground, there will be a pocket of air under the coffee filter that will slow it down, and that's going to skew your results. So we want to be detecting as it falls away from the detector, and we don't want to have to use data when the coffee filter is getting close to the ground and pushing on that pocket of air.